sound waves in the Sun are expected from the European Space Agency's SOHO mission. The sounds can't cross the near vacuum of space, but special telescopes detect visible vibrations as the Sun sings to itself. The notes and resonances reveal the behavior of its invisible interior. The probing of the Sun enters a new phase with SOHO. It goes to a vantage point 1.5 million kilometers out on the sunny side of the Earth. No night and no clouds interrupt the view of the vibrating Sun for years on end. Unprecedented fidelity, scientists may figure out why the Sun varies so much. Some years it's spotty and stormy, other years clear and quiet. More gradual changes seem to affect the Earth's climate. To understand our own planet, scientists must know the Sun better. SOHO stands for Solar and Heliospheric Observatory. It's the first observatory to explore the Sun all the way from its hot interior through to its brilliant surface. Into the stormy atmosphere, out to the region where the Sun's wind blows close to the Earth, on towards far-flung places where the wind falters and surrenders possession of cosmic space to a breeze from the stars. SOHO may discover the shape of this gigantic bag of solar wind, the heliosphere. The Sun gives off invisible ultraviolet light. Enough penetrates to the Earth's surface to change the color of a sunbather's skin. But the air blocks most of it. Only in space can telescopes register ultraviolet rays properly. SOHO carries a number of ultraviolet telescopes for investigating the Sun's atmosphere. How come it's far hotter than the bright surface? Ultraviolet rays pick out a key region, low in atmosphere, where temperatures start to soar. How lumpy is the atmosphere? The spacecraft maps variations in density by comparing ultraviolet light from different atoms. Why does the Sun keep blowing off its solar wind? SOHO watches puffs in the atmosphere as they gather speed and depart from the Sun. And a telescope using ordinary light is designed to trace the faintly visible atmosphere, or corona, out to a record-breaking distance, perhaps 20 million kilometers. SOHO detectors can identify the atomic particles of the solar wind. They travel onwards until they slam into the Earth's magnetic shield. There, the 4 satellites of ESA's cluster mission, orbiting the Earth together, are designed to observe what happens close to home. The scientists of SOHO and cluster will compare notes constantly. Built in Europe, SOHO is part of a transatlantic program to study the Sun and its effect on the Earth. ESA contributes 70% and NASA 30%. NASA launches ESA's spacecraft and provides links and special equipment. In return, US experts head 3 of SOHO's scientific teams. 9 experiments are led by Europe's own scientists. All the ingenious instruments find their own ways to explore the Sun. But SOHO's best chances of clearing up old mysteries and making new discoveries may come when the 12 teams compare their results from the far-flung solar wind to the vibrations that reach to the Sun's hidden heart. Our ancestors worshipped the Sun. They knew perfectly well that it rules the Earth. And many temples and churches still point to the rising Sun. Today's devotees are solar astronomers and space scientists who stand in awe of the Sun's vigor, its violence, and its variability. They know how it powers life. Green leaves act as photoelectric cells, absorbing the sun's rays. They know how it powers the world's weather, mainly by heating the tropical oceans. But the sun's own weather still baffles the scientists. The dark sunspots are scenes of intense magnetism. Great loops in the sun's atmosphere, shaped by magnetic arches, can trigger a magnetic explosion. A solar flare has the force of 1 billion H-bombs. There's widespread concern about the Earth's changing climate. That gives a special urgency to solar research. Some experts doubt whether the recent warming of the Earth is really due to carbon dioxide. Danish scientists have suggested that a speeding of the sun's activity seems to match the changes better. Whether that's right or not, records of a changeable sun show many variations from one century to the next. Who can understand the Earth's environment without sufficient knowledge of the sun that powers it? Some rays from the sun penetrate even the rocks of the Earth. In an underground laboratory at Gran Sasso, Italy, a tank of liquid detects particles called neutrinos coming from the very core of the sun. But many features of the sun's behavior are invisible from the Earth's surface. Only spacecraft can discover them. The Japanese SOHO satellite monitors X-rays that come from the sun's hot atmosphere. And the European Space Agency is leading a succession of solar missions conducted in partnership with NASA. Instruments in the European Retrievable Carrier Eureka monitor changes in the sun's output of energy. ESA's Ulysses spacecraft has flown for 5 years to travel over the sun's poles and observe its wind and its magnetic behavior from new angles. 4 satellites called Cluster have been designed to gather between them a 3-dimensional view of what happens when the sun's electric wind collides with the Earth's magnetism. ESA's largest solar spacecraft, SOHO, will stare at the sun itself to try to find out how it works. Scientists know that nuclear reactions in the sun's core produce its energy. The energy fights its way through a seething mass of electrified gas, encumbered with magnetic fields, towards the sun's visible surface. But details of the sun's behavior defy attempts at clear explanations. 2 main ideas inspire the instruments in SOHO. Sound waves in the sun, exaggerated here, reveal its internal makeup. For its atmosphere, ultraviolet light may hold the key. Although every spacecraft escapes from the air, which blocks out most ultraviolet rays on the Earth, SOHO also evades the ultraviolet glow of gas that surrounds our planet. And 1.5 million kilometers out, bathed in the solar wind, SOHO gives a continuous view of the sun for years on end. That's ideal for recording the sound waves. In the workshops of Languedoc, delicate craftsmanship and fierce testing prepared the European Space Agency's new solar observatory for 6 years' endurance in space. The French prime contractor assembling SOHO leads an aerospace team spread across 14 countries of Europe. Italian colleagues, for example, looked after the spacecraft's supply of electric power, while Swedish engineers gave SOHO its voice in its system for communicating data back to the Earth. The mission is to operate instruments to scrutinize the sun under long-range control. Scientists prepared advanced telescopes in their laboratories for the engineers to install and connect up with tender care. The instruments account for 1/3 of the weight of the spacecraft, totaling 1,850 kilograms at launch. In 1995, SOHO crosses the Atlantic. Under a deal with NASA, an Atlas rocket sends it into space. Then, Europe's spacecraft journeys for 4 months to escape the disturbances caused to Earth-orbiting satellites by the Earth itself and by the Moon. Nature offers a suitable destination 4 times farther off than the Moon. It's Lagrange point number 1, named after the French mathematician who 200 years ago predicted a zone where the gravitational tugs of Earth and Sun would be in balance. Here, the spacecraft can remain, circulating very slowly, like weed in the Sargasso Sea, while it keeps in step with the Earth's motion around the Sun. Uninterrupted sunshine, lapped up by the solar panels, power the spacecraft. Signals from the spacecraft are received for altogether 12 hours every day at NASA's deep space tracking stations. During each period of communication, tape recorders release data stored since the last session. SOHO makes special observations that generate data at high rates for 8 hours daily and a sustained campaign of 2 months each year. The spacecraft is fully stabilized, and every 2 months its thrusters adjust its orientation. To fulfill the scientists' hopes, SOHO must gaze at the center of the Sun's visible face, and its telescope eyes may wander by no more than a few thousandths of a degree. Europe's spacecraft SOHO will record sound waves in the Sun to find out what really goes on behind that shining face. Scientists know that a natural nuclear reactor lies at the very core of the Sun. The energy it releases worms out through a calm region of electrified gas towards a turbulent outer layer. Here, the gas wells up, carrying heat to the bright surface, where magnetism causes the stuff of the Sun to writhe and erupt. Different parts of the Sun rotate at different rates, which may be the reason for the magnetic turmoil. The fast-moving parts may drag the magnetism with them as they turn. They wind it up until it bursts through the surface and disperses the stress in great upheavals. But the picture of the Sun's interior was just a theory, until scientists detected motions of its surface due to sound waves of sharply defined pitch. In this, the Sun resembles a glass sphere that resonates with a clear note. A typical oscillation of the Sun takes 5 minutes, 10,000 times too low for human hearing. The sound waves follow curving routes. While some waves skip through the outer layers, other vibrations reach deep into the interior. When scientists interpret them, the Sun's sound waves disclose its hidden structure. They confirm the theorized layering, but they make the turbulent layer considerably deeper. It's like using seismic waves from earthquakes to reveal layers hidden deep underground. So scientists call their solar version helioseismology. It shows them the Sun's internal workings as nothing else can. But high-fidelity rendering of the Sun's sounds requires uninterrupted recording for months on end. SOHO's station on the sunny side of the Earth offers years of continuous observation. French experts built the instrument called GOLF, with help from Spanish colleagues, Danish, German, Swiss, Dutch and British scientists are co-investigators. GOLF watches the whole Sun and spots outward and inward movements. Sodium vapor absorbs yellow sodium light from the Sun and releases it sideways to the detectors. A magnet splits the light into different wavelengths. If one is stronger, the Sun's surface is moving towards SOHO. When it recedes, the other wavelength dominates. GOLF detects the sound waves that penetrate deep into the Sun's core. Another instrument divides the Sun into regions and detects the sound waves as a strobing in brightness. Scientists from Switzerland, Norway, France, Belgium, Spain and ESA make up the Virgo team, and they monitor the Sun's output of energy with a dozen other sensors. Mind-boggling recordings of many more sound waves will come from the Solar Oscillations Imager. A team of American experts created it for SOHO, and it detects motions of the Sun's surface at 1 million points. twin images of the Sun seen by the red light of nickel travel to the electronic camera by different routes, and their light waves may add together or cancel. In bright patches, the Sun's surface is rising. In dark patches, it's subsiding. The imager generates a picture a minute, creating a flood of data that SOHO's communications link to Earth can handle only during allotted periods each day, except in special non-stop programs lasting 2 months. In the sequences of images, supercomputers will find many thousands of different resonances that probe the turbulent layer beneath the bright surface. When SOHO eavesdrops on the singing Sun, what will be the biggest prize? Possibly the first clear signs of how the Sun creates the magnetism which dominates its outward behavior. Where the turbulent outer layer moves over the interior, is there a dynamo at work? Some astronomers study the Sun's behavior by visible light. Others use radio waves, which show a much broader object. And X-rays give spectacular pictures of the hottest part of the Sun's atmosphere. But ultraviolet light is the choice for ESA's SOHO mission. A battery of ultraviolet telescopes aboard SOHO explores the Sun's corona from its far outer regions down to its base. At the radiant surface of the Sun, the temperature is less than 6,000 degrees, but it soars to more than 1,000,000 degrees high in the corona. Hot regions boil up like thunderstorms and create differences in temperature and density from place to place. No one really knows what superheats the corona, but the surge in temperature begins at the top of a shallow, colorful region, the chromosphere. This mysterious transition zone radiates shortwave ultraviolet light. The Extreme Ultraviolet Imaging Telescope in SOHO is the work of French, Belgian, and American scientists. The image builds up on a silicon chip divided into 1,000,000 picture elements. One part of the telescope is coated to pick out rays emitted at 60,000 degrees. A rotating mask selects other parts, favoring emissions produced at 1,000,000 degrees or higher, farther out in the corona. Each part of the telescope reveals a different environment. In regions that seem most interesting, an instrument called SUMER can select the ultraviolet wavelengths more precisely. Made in Germany, with help from French, Swiss, and American scientists, it has a grating to split the rays into a spectrum, while a tilting mirror selects the lines for examination. Shifts in the lines measure the rapid motions in the region examined. A broadened line gives an impression of turbulence. Comparisons between pairs of lines can gauge the density of the source. By scanning across the Sun, SUMER builds up images strip by strip. Its chief target is the inner part of the corona, down to the transition zone. Hotter regions in the corona can yield their secrets to SOHO's Coronal Diagnostic Spectrometer, which splits the shortest wavelengths by letting the rays graze a grating. Scientists in the United Kingdom developed this instrument in collaboration with colleagues from Germany, the USA, Switzerland, France, Norway, and Italy. Scanning small squares on the Sun, it makes observations similar to SUMER's. There's more emphasis on measuring small-scale variations in density in the corona by comparing intensities at different wavelengths. The ultraviolet telescopes in SOHO should reveal how the writhing magnetic atmosphere of the Sun achieves its 1,000,000-degree temperatures and how it expels the particles of the solar wind into space. The streak marks that a child puts around a painting of the sun may come from folk memories of the corona seen during rare total eclipses. To study this faint atmosphere, Europe's SOHO spacecraft carries coronagraphs which blot out the bright surface with an artificial eclipse and give a side-on view of the corona around it. The ultraviolet coronagraph spectrometer reaches out to 7 million kilometers. Italian, Swiss and German scientists join the American leaders in the experiment. Disks and baffles hide the sun's glare, and a telescope split in 3 sends the rays to different detectors. One observes magnetism by visible light, another uses ultraviolet to recognize chemical elements, whilst the other picks out the typical ultraviolet coming from hydrogen atoms in the sun. With these sensors, the scientists can decode the chemistry and speed of motion in the sun's gases millions of kilometers out. Scientists want to relate the motions to the sun's weather closer in, trying to discover what drives the solar wind. Out to 21 million kilometers from the sun's surface, where the corona is extremely faint. A Franco-British telescope traces the streaks of the corona back towards their source lower in the atmosphere, where a German instrument peers closest and in greatest detail to within 70,000 kilometers of the bright surface. LASCO's all-seeing eyes may help to solve the riddle of mass ejections. When the sun flings out a mass of fast-moving matter, the storms it causes reach far. SOHO can detect electric particles from the sun, sweeping past it at hundreds of kilometers a second. Celius, a joint German, Swiss, American and Russian experiment, observes this solar wind. Selecting particles that worm through an electric trap, it measures their time of flight between 2 detectors. One sensor identifies the chemical elements in the solar wind. Another measures their electric charges. A third sensor counts rarer and faster particles from solar outbursts. They come in at an angle along the magnetic field. The sun's magnetism, dragged into space by the solar wind, slants because of the sun's rotation. The most energetic particles travel almost as fast as light. The CBAC detectors greet them. Clever little devices distinguish hydrogen, helium and electrons by tracking them through sandwiches of semiconductors. This instrument, made in Ireland, and this one, in Germany, select particles in a different energy range. Sensors from Finland broaden the search to lower energies and to higher energies. These fast particles and those in the commonplace solar wind are all specimens of the sun flung into space. SOHO enables scientists to trace the chemical packets back to their origins, sometimes in quiet conditions, sometimes in explosive outbursts. And they can check their theories about what propels the particles. SOHO gives early warning of the solar wind due to reach the Earth's vicinity an hour or so later. That will help scientists using Europe's 4 cluster satellites to study the impact of the solar wind on the Earth's magnetic shield. Like a watchful sentry, SOHO can link events near the Earth to outbursts from the sun's surface. The name of Europe's SOHO spacecraft stands for Solar and Heliospheric Observatory. The heliosphere is a bag in space filled by the electric wind from the sun. The Earth swims deep inside it, and it's streamlined by a breeze of gas from interstellar space. The sun lights up the hydrogen atoms of the interstellar breeze, creating an ultraviolet glow. But the heliosphere's shape depends on whether the sun's own wind is equally strong in all directions. Scientists from France and Finland are checking that with twin sensors of the SWAN experiment. As they scan the sky, hydrogen atoms in a chamber tune the sensors to the glow of the interstellar hydrogen. SWAN looks for a weaker glow downstream, which gives clues to the bag's shape. It's wide over the north and south poles if the solar wind is equal around the sun. But if the wind from the polar regions is weaker, the heliosphere is squashed above and below the poles. The interstellar breeze flattened the bag on both sides. Knowing the true shape should help scientists to tell how the heliosphere partly shields the Earth from cosmic rays coming from distant space. Then they may explain the episodes in past centuries when more cosmic rays reached the Earth and the world was cooler. If the life-giving sun becomes feebler from time to time, we had better know why.
I guess you're about the only person around that doesn't have TV coverage of the scene.
That's all right, I don't mind a bit.
They've got the flag up now, and you can see the stars and stripes on the lunar.
Are you getting a TV picture now, Houston?
Neil, yes, we are getting a TV picture. You're in our field of view now.
That's one small step for man,